Hello, fam. This is our last lesson in Unit 3. We are talking about assessing normality today. So we have talked about being able to solve problems using a normal curve and a standard normal curve. And hopefully at this point you're seeing the usefulness of both, being able to estimate percentages using the empirical rule for any normal distribution, but then also being able to find areas, proportions, and percents on a standard normal curve. So hopefully we're all feeling like we have some understanding of why that is important or useful. The thing, though, that we are discussing today is all of that depends on whether or not the distribution is normal. The empirical rule and finding areas using the standard normal curve, we can only do that if the problem tells us that the distribution is normal or approximately normal, or if we determine that the distribution is normal. So if you go through all of the problems that we did for standardizing, and I'll try to be quick so that we're not spending a ton of time reviewing. But if you go through all of these problems, each problem tells you that you are working with a normal curve. So here we have a distribution that is approximately normal. On our next one, we have a the size of the lids follows a normal distribution. Then this is another of the lid supplier. Then on the back we have tigers. The distance that tiger's ball travels follows a normal distribution, and the CDC heights of 3-year-olds are approximately normally distributed. And if you go through your Can You Do, you will find the same thing. Every problem that we've done where you are using a normal curve or a standard normal curve, we are told that the distribution is normal. So what do we do if we're not told that, and we have to decide on our own if a distribution is normal? So we are going to need information about that distribution because we know 3 characteristics or conditions of a normal distribution, and we're going to need to check those. So our first condition or our first characteristic is that the shape of a normal distribution is symmetric, unimodal, and bell-shaped. And all of those indicate something specific and different, meaning you can have a symmetric shape that's unimodal, but not necessarily bell-shaped. Bell-shaped is that very specific curve. So I would challenge you to think of a distribution that is symmetric and unimodal and not bell-shaped. It's possible. So symmetric, unimodal, bell-shaped. And that bell-shaped is one of the most important things. It has to have that curve because within that curve, we can say that most data is within 3 standard deviations of the mean. So that's another characteristic or condition. Most of the data is within 3 standard deviations of the mean, and that is what forms the bell shape. We know this as the empirical rule, or the 68, 95, 99.7 rule. You also need to know that as the empirical rule, because sometimes it will just refer to it as the empirical rule. One thing that I want to mention before I get too far ahead of myself is if you're going to abbreviate standard deviation, make sure that you are using STD-DEV. That is the only appropriate abbreviation for standard deviation. And you know, it's funny, in stats, they're not very picky about your rounding. They're not picky about whether or not you use an approximately equals or an exactly equals, but they are picky with you abbreviating. So do not use abbreviations unless you know that they are the correct abbreviations. So 2 characteristics or conditions, we got symmetric, unimodal bell-shaped, we have the empirical rule, and then lastly, we have that the mean and the median are approximately equal. I have an and there. I don't really know where I was going with that. So I'm just going to white out that. So we have these 3 things happening. These are our main conditions. So if we're going to check these 3 things, we're going to need to know a fair amount about the data. In fact, in a lot of cases, we're going to need to have the entire data set, which is what we have here in our example that we're going to use to assess normality. So the measurements listed below describe the usable capacity in cubic feet of a sample of 36 side-by-side refrigerators. Are the data close to normal? So what they're saying is how big, essentially how big is your fridge? When they say side-by-side, what they're meaning is the freezer is on one side and the fridge is on the other side. A lot of us have fridge on top, freezer on bottom. So step number 1, let's address the shape issue. So we need to plot the data. And because of the decimal situation we got going on here, I think that the best way to plot this would be to make a histogram. So we're going to go into Stat, 1 for edit, and then we are going to enter in this data. I have it entered, so you should pause the video and enter this data for yourself. Remember, you have your cumulative test coming up and you may be asked to find a histogram on that. So don't just let me do all of this work for you. Actually go through and enter this into your calculator. Once you have that entered, we're going to second y equals. You're going to want to make sure that only one of your plots is on, and I always just use the one that's on. Our histogram is our 3rd option in the type, and mine was in list 4. Remember, you can't just type in L4. You have to hit blue button 4. And then from here, I'm just going to hit graph. Check number of data points needed for the calculation. Okay. Let me go and check my list. Let us try again. We got, that's our histogram, right? Let me mess with my window really quick and maybe that'll fix things. Your X, oh, my X scale is messed up. I should have read that first. Do you guys see here how it's saying my X scale is bigger than or less than or equal to 131? So something's the matter with my window. So maybe this X scale is too big. So maybe I should change it. I meant too small. So maybe I should change that to 1. I'm only not pausing this and figuring it out myself because I want you guys to see that you can problem solve when you're having issues with your calculator. Like, I'm not the only one that can fix your calculator. You can do the same exact thing that I'm doing. So I didn't read the error at first because whatevs. But then once my usual tricks didn't fix it, I actually read the error, and I think what was happening was my X scale was too small. So for some reason, my X scale was 0.02. So I changed it to 1. Let's see if that fixes it. It did. Now remember, when you can't see the graph correctly, you're going to hit zoom stat, which is zoom 9. And then we're not quite done, because from this window, we go in and adjust or from this view, we go in and adjust our window. So we're going to hit window button. So I'm going to make my X min 12. And you guys know that I like to write this down. So my X min I changed to 12. My X max I'm going to change to 20 because I like to have nice whole numbers. My X scale I'm going to change to 1. And now I'm going to graph this again. So right from this window, after I type in that 1, I'm going to hit graph again. And I cannot hit zoom stat here, because if I hit zoom stat here, it's going to change my window back to what it was. See how it changed it back? So when I go back into my window, now all of those numbers are the same. So 12, 20, 1. I'm not quite sure why that fixed it. No, I don't think that fixed it. 12, 20, yeah. 1 graph. And see how it's still cut off? So now I'm going to go back into my window and change my Y max to 15. Because it's getting cut off because I'm not letting my graph go high enough. So I'm changing my Y max to 15. And anything I change, I write it down just as reference. And now it's perfect. I talk about how, depending on your scale, your histogram might look different. So I'm going to check one other X scale. I'm going to see what an X scale of 1.5 looks like. I don't really like that one as much. And I'm going to see what a scale of 2 looks like. No, definitely no. And maybe I should check a scale of 0.5. Do you have to do this? No, I'm just checking. Yeah, that's too many bars. So it looks like 1 is probably our best option. That's enough bins or bars, not too many bars, not too few. This is a really good graph. So now we're going to build our histogram. That line's not very straight. Come on. So I know what my min and my max need to be on the X because I wrote it down here, 12 and 20. So I'm going to just start at 12. Go over till I get to 20. My bins are getting too big. Then I want to make sure I label this as usable capacity. This is feet cubed. Then I personally chose a Y max of 15. that's kind of a lot to fit here. So I think I'm going to go in to my graph, hit trace, and see how many is in my tallest bin. In my tallest bin, I only have 11. So I'm just going to try to get to 11 tick marks. Okay. And I think that I might label 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I'm just going to label that. This is frequency or count. And now I'm going to go over to each bin and use my number here to tell me how many is in each bin. So from 12 to 13, it's 1. From 13 to 14, it's 1. From 14 to 15, it's 6. And I am going to leave it as gather your thoughts, teacher. I am not going to give you the rest of the values. I want you to go through and actually be doing this. So I'm going to make my graph. I'm just not going to explicitly tell you what each value is. Because you need to be knowing how to do this. Okay, if you're not done, pause. I'm going to shade mine in for just a second and then get cruising. He's not perfect, but he's looking pretty good. I like to color in my bars just because I think it makes it look just a little bit better. Gives the graph a little bit of dimension, not that that matters, but... Okay, so we plotted the data to check, is it symmetric, unimodal, and bell-shaped? So it is unimodal. It is very nearly symmetric. It is very nearly symmetric. If I took this off of the top here and put it down here, it'd be exactly symmetric. So I personally would say that this is roughly symmetric, unimodal, roughly bell-shaped. I think we got a rough bell shape going on there. Our next characteristic or condition is checking if the mean and the median are equal. So we're going to go in and find those summary statistics. So to do that, we hit stat, calc, one variable stats. My stuff is in list 4. And these are my stats. So our average or our mean is 15.825. Our median is 15.9. And our standard deviation is 1.22. These two values are very close in value. 15.8 and 15.9 are very close. So I would say that those are approximately the same. So first condition, shape. Second condition, mean and median, and then it's the third condition that's a doozy. Now we need to check, is most of the data within 3 standard deviations of the mean? And we are going to go even further and use the empirical rule. We're going to check, is it close to 68, 95, 99.7? So in order to do this, we need to figure out what those values are. So we need to figure out the lower bound and the upper bound, that is 1 standard deviation below and 1 standard deviation above. So how we do that is 15.825 plus or minus 1 times our standard deviation. So this is our mean minus 1 standard deviation and our mean plus 1 standard deviation. So our mean minus 1 standard deviation is 14.605. I'm just going to write a comma, or maybe I should write 2. And our mean plus 1 standard deviation is 17.045. So now we go up to our graph and we're going to mark those values. So 14.605. So where would we mark this? Well, it has to be 14.605, so we would mark in between 14.6 and 14.7. And then 17.045 would have to be between 17 and 17.2. So this is between these two tick marks is 1 standard deviation from the mean. The mean is right here. So I'm going to mark that. The mean is right here. This is 1 standard deviation below. This is 1 standard deviation above. So what we now need to do is count how many values that is. So you start at the 1 below and you count to the 1 above. So 1, 2, 3. I'm getting 24. So down here it says, well, how many observations are between the first, or I should say, how many observations are within 1 standard deviation? 24 out of 36, which translates to 0.67 or 67%. That is very close to 68. Because remember, we're checking the 68, 95, 99.7 rule. Okay, so now we're going to see what are the boundaries for 2 standard deviations. So 15.825 plus or minus 2 times 1.22. This is going to give us a lower bound of 13.385 and an upper bound of 18.265. So just like I did before, I'm going to go up and mark these values in the distribution. So 13.385 would take us all the way down to between 12.9 and 13.7. Then 18.265 would put us between 17.9 and 18.4. And just like I did on the last one, I'm going to mark this. This is 2 standard deviations below. This is 2 standard deviations above. And if you count those now, you have to count from these new marks that I made. So from this line to this line, that is 34 out of 36 of your observations. That translates to 0.94 with a bar, which is 94%. So we're still very close. 67 compared to 68, 94 compared to 95. So now we just check our last standard or our third standard deviation. So we do 15, 8, 2, 5 plus or minus 3 times 1.22. And I'm not going to fill in those values for you. I'm not going to fill in those boundary values. And I'm not going to fill in this section because I want you to be doing something on your own. So now that we've checked those 3 conditions, we start by saying, okay, we know that the conditions or the characteristics are shape, center, spread. So we go through and check the shape, symmetric, unimodal, bell-shaped. The center, are the measures of center approximately equal? Spread, is the spread roughly 68, 95, 99.7? Then we decide, what do we conclude? Are the data close to normal? Notice it's asking us, is it close to normal? They're not saying, is it for sure normal? They're saying, is it close to normal? Sorry, I don't want to use that color. My highlighter got stuck. And our answer is yes. The distribution of refrigerator usable capacity is approximately normal, or I could also say close to normal, because the percents 68, just kidding, 67, 94, and 100 are close to the empirical rule. Very close to the guidelines for the empirical rule. The histogram is roughly symmetric, bell-shaped, and unimodal, and the mean and median are approximately equal. So that's one way to determine normality. When you check these, there's no specific order. Like if I had to make this worksheet again, I would have started with shape, center, spread, but I started with spread, then shape, then center. The order doesn't matter as long as you're addressing all 3 things. So this is one way. Let's zoom out. Our video currently is 29 minutes long. So to check if that data set was normal, 29 minutes later, we can conclude yes, based off center, shape, and spread. Now, when we're in an exam situation, if we get a question like this, there is no way we can burn 30 minutes trying to decide if a distribution is normal by this process. So there is a shortcut. You need to know that this is how you would check. You need to know that, okay, if I had to take an entire data set, I would need to plot it, run the summary statistics, calculate the spread in terms of the empirical rule. The shortcut, though, is checking the normal probability plot. So over to the side, at the very bottom, over to the bottom right, there is a normal probability plot. This is a normal probability plot of the usable capacity for the refrigerator data. What characteristic about this plot stands out to you? So remember, when we talked about characteristics above, we talked about shape, center, spread. So think about the shape, the center, the spread, and see, is there anything about this plot that you're like, huh, okay. Okay, hopefully you were able to come up with something. What I'm hoping you will recognize is it is linear. It is linear. Meaning it looks like a straight line. I think that that is a pretty distinct shape for this graph. It looks like a straight line. Now, is it exactly linear? No. So we should probably note that it's approximately linear. But if I'm looking at this graph, what I am noticing is that is very, very close to a straight line. Well, now we can make an inference, or we can make a hypothesis. And my guess is, if I have a data set and the normal probability plot looks linear, then my data is probably normal, because we know that this data is approximately normal, and look at its normal probability plot. So we know this is approximately normal, and it ends up having a normal probability plot that looks like a straight line. So I bet you if we do this for a set of data, if it's a straight line, it's approximately normal, and if it's not a straight line, then it's probably not approximately normal. So that would be my hypothesis. So now we're going to formalize that on this paper that is called the normal probability plot. Now this part of the lesson is not quite as long as this part, or at least I'm hoping that it's not. So I think what I'll do now is end this video so that you have kind of two shorter ones instead of one long one, and that you can take a break or do what you need to do, so that when we go over this worksheet, you're feeling like you're good to go. Okay, so love you. See you soon.